Hello everyone. In this video, we will be studying the concepts of iterable and iterator, and also we'll be getting an overview of interfaces. But the actual goal with which we will determine whether this video was successful or not would be to implement pre-order traversal of a generic tree using only a for each loop. So before moving on, let me just show you the agenda of what we're going to discuss today. So first we'll discuss the for each loop. Let's forget about the remainder of this list. Let's start with the for each loop. So I'm sure that when you were coding, you must have written something of this sort. This is basically a for each loop, which is expected to loop over all the elements in a certain structure called GT, for example, which I'm going to say use to represent my generic tree. So the goal is to actually use this for each loop to traverse my generic tree in a pre-order fashion. I'm assuming you know what the pre-order traversal is supposed to mean. If not, then I would suggest you watch the previous videos where it has been explained pretty thoroughly. So this is what we're going to do. But for this, we need a generic tree class, say this one. I'm doing this so that you don't feel confused with this root right here. I mean, if I had to iterate over this root, you would say, oh, wow, how are you iterating over a root? I'm not. I'll be iterating over the entire tree and printing it in a pre-order fashion. So now that we have actually made this object, this GT object, we need to, well, traverse through this generic tree, for which we need a generic tree class. Class generic tree, and say we have a node root with us and a constructor. We have a root as our parameter, and that's basically the generic tree class. And well, I say that this should be enough to simply print all our values. Let's try to run this code and see what we get as output. Now we've gotten some error. We'll analyze that in a bit. To understand this error, we need to, well, understand the concept of an interface. We've seen our for each loop, we've seen our generic tree class. Let's talk about interfaces. So before we move on, I must warn you that this video is going to be more of an object oriented programming concept rather than a data structure and algorithm concept. So for this video, what we're going to do is we'll talk about interfaces as I just mentioned. And in interfaces, I'm going to start by the definition. An interface is basically a function that does not have a body. It's a function without a body. And that's basically what an interface is. So what happens is that when we define an interface, we expect a class to implement it. The class will write the body. The class will use the same parameters as we did in an interface. The class will use the same arguments, same return type, all of it. May sound confusing. I'll write a pseudocode which will help explain it better. Just understand this for the time being. Now that we've decided this, let me write it down. For example, this is how we define an interface in Java. Interface I, and well, it does not have a body. In an interface, let's write a function. Say it has two integers, digit 1, digit 2, and this function will not have a body. We've simply defined the prototype, and that's it. And that's our interface. Now, what we expect from a class, say class A, is to actually implement this interface using this prototype, which means that it will have the same return type, it will have the same parameters or the arguments, and the body will be implemented by this class. It will use the same format. And we will write some logic here to actually implement it. And that's basically how interfaces work. Now you might be wondering, what, we have functions already, we have classes already, why do we need an interface? To put it very simply, we need interfaces for uniformity, for modularity. Say you work in an organization and you are a developer. So there are two developers here, developer 1 and developer 2. Now, developer 1 writes some class called class 1. Developer 2 writes another class called class 2. Now, both developers need. Now, what happens is that, say, developer 1 develops a function called fun, and this developer is creating this particular function which will be used by developer 2. But developer 2 actually calls this function using fun, capital F. Now, it might be very obvious to assume that this won't work, but we need a solution to this problem as well, because dev2 doesn't really interact with dev1 as much. He just sees his code, his or her code, and they implement it in their own way. So for uniformity, what the tech lead can do is that the tech lead can create an interface. That interface can be defined with a uniform structure, say like this, and let's call it fun. What the tech lead does is that the tech lead sends this interface to dev1 and to dev2. And what that basically does is that this constricts the particular movement, you can say, the variation that both of the devs could have had in their code. For example, this spelling error. Now you see, when dev2 tries to run this particular code, it won't run, because the interface that has been provided to this developer is actually of this particular type. Now this function was implemented by dev1, and dev2 will have to use this same format if they want to use this particular functionality. And now this particular code has been divided into this module, which is derived from this interface. And that's basically the point of using an interface, to introduce modularity, to enforce a certain pattern while developing, which is considered a best practice in the industry. So that's basically the concept of an interface, an overview. Of course, there is a lot more to it when it comes to the implementation, which we will be seeing a part of in a moment. But when it comes to creating an object of an interface, well, for a class, what we do is create with my generic class. Right here, I simply created an object of this type. I named the class with my object name with the new variable, and again class name with my parameters. That's basically how you create an object. Now with my interface, the difference would be that I will write my interface I'll write my object name. What you would expect to do here is that you use a new operator, yeah, and create a new interface like this, but this is wrong. Instead, what we'll do is that we will define our interface like this, but this will be implemented using our class A that we implemented earlier. That is what we'll use to create an object of our interface. And that's basically how you define an interface. And that's all we need to know for now. Now, summarizing what we've learned about the interface so far, we have the information that interface is a contract of a function of a function that is to be implemented by a class, and well, it has a function signature as is the case with a normal function. And the way to introduce an object is, well, this way right here. And that's basically what we need to learn about interfaces to move forward in this video. So let me just erase that right now. Now, as we had noticed, there was an error in our code. This error says that for each is not applicable for this expression type, and what is required is this iterable class, basically iterable interface, which we will be implementing. So this is what we're going to talk about right now. Coming to iterable. An iterable is basically a function that is implemented by those classes that want to be looped. And that's basically what we want to do here in the first place. We want to use a for each loop to iterate over a generic tree. So implemented by classes that wish to be looped or iterated over. And that's basically what we wish to do. The best example that we have is the case in point, which is generic tree. Now, this iterable has only one function, and that function is, well, you may have guessed it, the iterator. So this iterator is basically a function that returns an iterator object. You see this error, iterable? This is what is required of us. So let's implement it really quickly and then see what we get from there. Implements iterable of class integer. Since we are assuming that the data type inside our tree is that of an integer, let's try to run this and see what we get from here. Generic tree is not abstract and does not override abstract method iterator in iterable, which is the function we talked about. So now we need to implement this particular function. And this function goes by the form public iterator, which is the object type that we have to return, which is of integer type. And the name of the function, as we discussed, was iterator. That's basically what's needed to be done here at the moment. But what we can also have here is the iterator object, which will we be returning in a bit. And this object, this is basically an object of this interface iterator. So since this is an interface, it needs to be implemented using a class, as I had just mentioned a few minutes ago. That class can be named, say, generic tree order. And then finally, we return this object. And that's basically how you implement an iterator. Now we need to implement this class, generic tree preorder. This class is actually expected to do all the heavy lifting for us. This will be handling all the traversals that we wish to implement in this particular video. And this class, in case you caught on, will implement iterator. Now, before we move on, it is important to discuss a few more details about the iterator class. This iterator class actually has two functions. Those functions are namely as next and next. Purpose of this functions is such that as next tells us if the next value is available. It tells us if the next value is available for us to traverse to or not. The next function simply returns the current value and it sets up the class to traverse to the next value. And so this is basically the two functions that we will be implementing. And let's try to do that. So in this class, we have a constructor. We will be needing a constructor, the purpose of which we'll see in a moment. And we need to implement the two functions that we talked about. First is as next, which will be of type Boolean, because we are actually telling the compiler whether we still have a value to traverse to or not. The second one would be an integer type function known as next, which will return the current value and set up the class for the next particular traversal. Now, coming to the implementation, we'll need to track our current integer, and in hasNext function, we'll check if this current integer is equal to null or not. If it is null, then we turn false. That means that there is no next particular value that we can traverse to. Otherwise, we return true. Now you may be wondering why am I putting an equality check on a null operator when it comes to an integer. So you see, we're using this integer class here, which is different from your small int that you're used to. What happens is that this capital one does not go into the program stack directly. What it does is that it creates an address for this variable, for the value of this variable, and it puts our value in the heap. And this particular thing can have a value as null. So we can use this for to our benefit and put this check here and return values accordingly. Now coming to next, which is actually traversing our tree, traversing through our tree. Now, in case you have been following this lecture series in order, you may have noticed a video previously where we implement the iteration of pre-order and post-order iteratively. So what I'm going to do here is that I'm going to copy and paste this code because the logic is basically the same, and I won't be explaining it in detail here. So if you want to understand how that particular function works, I suggest you go back to that video and see how it's being implemented. So I'll be back in a moment with that particular code snippet. All right, so now we have this function. This fr represents the value that says that, I'll store the value of the next particular variable in this variable. So next particular value in this variable, which represents the forward value. This nval is basically the value that we will be storing. So let's change this to nval as well, so that there is consistency in our code. Then we move this nval forward, and if it's not possible, we set it to null. That is, if we are at the end of our traversal, we set this value to null, this current value which we had previously. And the remainder of the code is basically the same except this one line. We were basically printing our pre-order value here. Instead, I am changing the value of nval to whatever I have in as my pre-order value at the moment. Then the rest of the code is the same, and we just don't store a post-order value here. We simply pop our value because we don't really need it anymore. And this particular value is returned at the end. Again, I suggest that you watch that previous video where we implement the pre-order and post-order traversal of a generic tree iteratively to understand this better. Now, this particular function requires a stack. So I think we can use our constructor for this purpose. Let's have, say, a stack here first. And now we can implement the stack. And we'll be needing a node here to input. This nval will have the starting point as a root, which will be the very root of the tree. And since there is a parameter in our constructor here, its call will also need a parameter. That parameter will be root, which is coming from here. And that's basically our implementation. But before we move on, I must mention that I have already defined this pair class, which we had in that question. This pair has two attributes. One is the node, another one is the state, which will be used to store our pre-order values here. So let's try to get an output first and see what we are getting at this moment with our current information. Code cannot be converted to an integer. All right. Okay, so we don't really need to implement this right here because we are already handling it in our next function. So instead, what we'll do is that we will simply push a pair in our stack to initialize it. This pair will have the value as root and its state as -1. With -1 represents the state as the pre-order state basically. And if the value is anywhere between 0 and the size of the child minus 1, my size of the children length, size of the children array list, this one right here, which we've seen multiple times in this generic tree series. This, if the size of this children, um, whatever we have it, say our size is equal to 5, if our state happens to be anywhere between 0 and 5 both included, sorry, 0 and 5 minus 1 both included, we will be in our in order section, which will be basically equivalent to the pre-order section for the children. This might sound a little confusing, but basically what's happening here is that first we traverse in pre-order fashion in this section of the code. Then we'll be in this range where the state is greater than or equal to 0 and less than the size of the children array list. We will increase the state and work on our children in pre-order fashion. And then once we're done, once we're in the post-order section, we pop the values from our stack. That is the summary of how to do this iteratively. And now let's try to run this. We might face a lot more errors because this is a lengthy code and it's pretty complicated. So, okay, our pair cannot be converted to an integer. That's because our stack is actually of type pair, not integer. And we need to update our symbol to nval, which is the new value. And I think let's try to run this again and see where we stand. All right, at line 117. That is because we haven't given an input. For our input, we can simply use one of the pre-made formats that we have in the generic tree section. Since that is what we're implementing at the moment, we'll go to generic tree. We can pick any question. A tree is basically created in this format. I'll draw this tree for you in a moment and show you what it looks like. Now let's try to run this. It's accepting. It's not printing anything at the moment. And we will see why. So one of the reasons for that is actually this section of the code right here. You see, when we are initializing our new val, it will initialize as null right here. Since we don't really have anything stored in an inval, it will be null. And so this fr variable, the forward variable, this will also return null. And if this value is returned as null, and if the value of nval is null, there will be no next variable to turn to. So what we need to do to fix this is to do this. We'll call the next function once so that we initialize our value at least once, and then we see where our iteration goes. And now you see this is a successful implementation of this particular tree. The input was of this form. Let me just draw the tree for you to help you understand it better. This tree is basically 10, 20, 30, then 50 is our child, then we go back up, We have 60 as our next child. We go up here and we have 40. This is basically our tree. So the pre-order for this tree would be, first we print 10, we go left to 20, then we go back up to 30, then we travel left again to 50, we go to right 60, and then finally we print 40. Let's see if this is our output. 10, 20, 30, 50, 60, and 40. So our implementation seems to be correct. But there's one other thing that I would like to point out here is that now that the for each loop is successful, this for each loop is actually not what it seems. I mean, of course, it's simpler for us to write, but it's in actually syntactical sugar, which actually depends on the iterator class. And as I mentioned, the iterate class has two functions, that is, well, has next and the next. So what we can do is create an iterator object, which let's call it GTI, which is generic tree iterator. And this will be basically, we'll be using this class here to implement it. And since we need our iterator object back, we will call the iterator function for it. Now that we have it, we can use the properties of has next and next with for us. Now we'll check if GTI dot has next is true or not. If it does, then we simply print the value that we had. This next function returns the current value that we have, so this will be printed. Let's try to comment this and see what we get. We might have to resolve some errors, but we'll figure it out. So that's our output: 10, 20, 30, 50, 60, and 40, which is basically the same as the output right here. So you see, what happens is that this for each loop at the back end is actually converted to this iterator. And this is basically how the functioning takes place. This for each loop is only for humans and to make the job easier for us, so that it's easier for us to write. But at the back end, this is what the functionality looks like. And that's basically how you implement the iterable and the iterator portions. And well, with that, this is the end of the video. I hope you gained a lot of insight. And again, personally, it took me a couple of tries, more than that actually, to understand this concept properly. So I would suggest, in case, it started to seep in your head, but it was missing out in like bits and pieces, I would suggest you watch it again and try to implement it yourself. That would really help the concept, because this is actually a very important concept, especially when you're looking forward to make a project in the industry. So I would suggest you watch the video again if you could not understand it once, then try to implement it yourself and try to understand why each section of the code is working the way it is. And that's basically it from my side. Thank you so much for watching. And well, if you liked the content, if you found it useful, leave a like, drop a comment, and subscribe to our channel.